All right, so today we're talking about the ideal gas law. Now again, if I go back to the four variables that we've been looking at for gases, so we've got pressure, we've got volume, we've got temperature, and we've got an amount. So far, like in the combined gas law, we actually separated the amount. We held the amount constant, and then we used just three variables, and we talked about how that can be maybe narrowed down to just two variables, and we also had some standard conditions. Well, if we start to say, well, what happens if this gets to change? That changes these. So we want to be able to have a formula that's going to allow us to use all four of these at the same time. Now, what we really should do is kind of talk a little bit about how the amount affects pressure, how the amount would affect volume, how the amount would affect temperature if we have the others held constant. So, for instance, if we make a container that's going to be rigid inside, so the volume is going to remain constant, and we keep it in the room so that the temperature remains constant, if we have some particles in there, let's go ahead and put some particles in here. Okay, those particles are going to bounce around, they're going to hit the wall, and they're going to create a certain amount of pressure inside the container. Well, if we increase the amount, so as the amount increases, we're going to see that if we put more particles in there, we're going to have a greater pressure because now those collisions are going to happen more frequently. They're going to push on the walls of the container, and so because you have more force acting per unit area, you're going to see an increase in the pressure when the volume is held constant and the temperature is held constant. Now we can do the same thing if we look at, say, let's make it a pressure constant. So now we're going to look at a container like a balloon, okay? And our balloon is going to be able to change its shape. So in other words, we're going to allow the volume to change now, okay? But the pressure is going to be equalized. So we'll have pressure inside the balloon, and pressure outside of the balloon will always be the same. As we increase the amount of particles, so again, I'm going to put some particles in here. If we look at that particle increase, okay, as we put more particles in there, we're going to increase the collisions. The collisions are going to happen more frequently, which means that instead of the pressure increasing, because we're going to maintain this as a constant, we'll see that the volume will increase. So we'll get an increase in that volume. And again, we're in the same room, so the temperature remains constant. So as we increase the amount, we see an increase in the volume. Now our last situation would be we want to hold the pressure constant, we want to hold the volume constant, and we want to see what's going to happen to the temperature. Okay, so I need to have a container that's not going to be moving. So we got to have a fixed container. Okay, and we want to have a pressure change. So this is going to be, we'll put a little valve on here. So in other words, when the pressure builds up, it will allow it to equalize so that we have pressure inside equal to the pressure outside. And then we look at putting in some particles. So as we put in our particles, okay, we've got a certain amount of pressure that's going on. We know that it's going to be, and this is where it really becomes a tough deal, because that release valve is really going to allow us to change the particles through here. So generally we don't see this as an example. There's not a good one, because like in the case of a container that we could seal off or a balloon that we could tie off, this container is going to have to maintain a little bit of an openness to it so that it can have a pressure that will adjust, so the pressure inside and pressure outside will be the same. We have the container with the shape the same so that the volume can remain constant. And so really what we're trying to do is say what's going to happen to that temperature. So as we increase our amount of particles, so we increase the amount of particles, we're going to expect the temperature hold on. Okay, so again, we're talking about the number of particles. So if we increase the number of particles inside our container, and again, we're trying to keep them inside the container, but allow that pressure to change, we would see that the collisions are going to happen more frequently, but because the frequency of those collisions is going to be more frequent, we actually would see that we need to balance our kinetic energy. So the velocity of them is going to have to go down so that we can maintain kind of a lesser amount of kinetic energy per particle on average. So we would actually see that the temperature would decrease slightly as we have more of them in there. Again, this is a pretty rare case to see this because the container would allow too much to escape. So that's really not a great representation of how amount and temperature play, but really we do see amount and pressure and amount and volume work quite well because of the way that we can actually do this in real life. Now all this goes together to basically say we have amount being in a direct relationship with pressure and volume, and we have temperature being indirect, so we have this proportionality between them that comes out to be like this. Where this is our ideal gas law. So pressure and volume would be inverse relationships with each other, okay, and would be in a direct relationship with the amount. And the temperature will be an inverse relationship with the amount, but will be in a direct relationship with the pressure and the volume. So we're kind of setting this up in this. Now, the R is the unique thing to this. This is called the gas law constant, okay? And what it really is it's kind of like the combined gas law in that this is the representation of the standard conditions. Okay, so this is our standard conditions. So it kind of combines all of the standard pressure, the standard temperature, the standard volume, and the standard amount. Now, the standards for each of these, so if we talk about standard pressure, is 1 atm, and the standard volume, the standard temperature is 0 degrees Celsius or 273 Kelvin. We haven't really talked about what the standard volume would be or the standard amount. Now, typically when we talk about a standard amount, we like to talk about 1 mole. It's the same way that we standardize talking about molar masses. So that means that there's got to be a fixed volume that will fall for these conditions. And there is, and that's the standard molar volume. It's 22.4 liters for 1 mole at 1 atm at 0 degrees Kelvin. So that's actually on your green sheet as well. So we do have our standard conditions. Where is it? The molar volume of any gas. Oops. Make sure we have it up high enough. Molar volume at any gas at STP is always going to be 22.4 liters per 1 mole. So that's the standard conditions. Now, because we're using that as a constant, we're going to see that there are some gas constants right here. And so this is the R value that we're going to use. And those R values are really dependent upon the types of units that we're dealing with. So in all situations, we're dealing with moles, moles, moles. We're dealing with Kelvin, Kelvin, Kelvin. And we're dealing with liters, liters, liters. So the only change that we see in this gas law constant on your sheet is the pressure unit. So this one would be used for ATMs. This one would be used for millimeters mercury. And this one would be used for kilopascals. So we have a gas constant that we can choose based upon what the pressure units are in the problem. Okay, and so that's really how this equation kind of breaks down. It is, again, always going to be pressure in choice, volume in liters. The N represents the amount, okay, that's the moles, and then the T needs to be in Kelvin. So again, that's how we break down this equation. So as we kind of move forward, we'll go through a couple examples. and we'll see how this kind of works. So let's look at our first one. So I've got here a sample. Put it right there. Okay. A sample of a gas that occupies a set volume at a set temperature. And they want to know what is the pressure in atmospheres given that there are this many moles of the gas in the sample. So I like to do this first. I know that I'm going to have to deal with these 4 variables, or these 5 letters, I should say. So I'm going to list the letters out. So P equals, V equals, N equals, R equals, let's get this up a little higher, and T equals. So my pressure was, what's the question? So the pressure is the question mark. The volume was given to me at 8.77 liters. The N is given to me in my amount of moles, so 1.45 moles. The R I'm going to choose, okay, and this is going to be, it said I wanted an ATM, so I'm going to go back to my green sheet. I'm going to look at my values. I want the one that has the ATMs in it, so it's 0.0821. And that would be in liters, atmospheres per moles Kelvin. And then they have a temperature given to us, and so the temperature was 20 degrees Celsius. So we're going to need to add 273 to that to get that turned into Kelvin. So 293. So now once we have all of our information kind of listed out and given to us, we can now go through and set up and solve this. So again, I like to write down my equation on my paper. So PV equals nRT. My pressure is my variable. My volume was 8.77 liters. My N is 1.45 moles. My R is 0.0821 liters, atmospheres per moles Kelvin, and my temperature is 293 Kelvin. So from a units point of view, the moles are going to cancel, the Kelvin's going to cancel. We're going to divide by our 8.77 liters. So the liters are going to cancel, and we'd be left with something that'll be an ATM. So now the only thing we have left to do is to grab a calculator and go through and solve this. So I've got my 1.45 times 0.0821 times 293 divided by 8.77. So it looks like I'm going to get an answer for my pressure that'll be equal to, and again, 1, 2, 3, 1, 2, 3, 1, 2, 3, so 398 ATM. Okay, so we'll go through a couple more examples so you'll get a chance to see how we can use this. So let's do another one. Okay. Here we go. We've got a sample that contains this many moles of a gas, and it's at a certain temperature. It has a certain pressure. Now we're looking for the volume. So again, I'm going to go through and I'm going to list out my given and my unknown. So I'm doing P equals, V equals, N equals, R equals, T equals. My pressure is 0.857 ATMs. My volume was what's in question, and I'll give this in liters. My moles was 4.38 moles. My R value, okay, I'm going to use that one that matches the ATM, so 2, 1. Again, this is liters ATM per mole Kelvin. And then my temperature was in 250 Kelvin. Okay, so I'm going to go back and set this up. So this is my PV equals nRT. My pressure 0.857 ATMs. My volume was what we're looking for. The N is 4.38 moles. The R I chose to be 0.0821. And then my temperature is 250. Okay, and again, the kelvins will cancel, the moles will cancel, the ATMs will cancel when we divide. So that we can then get our volume. So this is where we just grab our calculator now. And we're doing our 4.38 times 0.0821 times 250 divided by 0.857. And that gives us a volume then of, let's see, 1, 2, 3, so 105 liters. Okay. On to another example. So let's look at another one again. So here we are going to go with this one here. So again, they're looking at what is the pressure. Again, they want it in atmospheres, so we're going to keep that same gas law constant. We know the moles, we know the volume, and we know the temperature. So we're going to go through and just write down what we know again. So I list the P, the V, the N, the R, the T. My pressure is what's in question in ATMs. My volume was 4.08 liters. My N is my moles, so 0.325 moles. My R is my choice. That's ATM liters per moles Kelvin. And my temperature then is 35 degrees Celsius. We're going to need to add 273 to get that into Kelvin. So that's 308, I believe, Kelvin. Okay, we go back to our equation. So again, it's a PV equals nRT. And now all we do is we plug our values in. So pressure is my question. My volume was 4.08 liters. My N is 0.325 moles. My R value is 0.0821. My temperature is 308 Kelvin. We're just solving now for the pressure. So we're just going to divide by it. Then we just get a calculator again and we do this. So 0.325 times 0.0821 times 308 divided by 4.08. So it looks like our pressure comes out to be, and again, I think we're in 3 sig figs, so 2.01 ATM is our pressure. Okay. Now I've got one more example because so far we just saw things that looked at trying to solve for either the P or the V. We should look at one that does something for the other side as well. So let's go ahead and we'll look at one here. This one now has the question, how many grams of carbon dioxide are there in a certain volume, certain temperature, and certain pressure? So I'm going to go ahead and I'm going to write this one down. So this is a little bit different because now we're looking for a mass. But I'm going to do my P, my V, my N, my R, and my T. And I know the pressure. I know the volume. I don't know the amount. Okay, this is where I don't know my moles. Okay, but I do know that it's carbon dioxide as the type of gas. The R I'm going to choose is based on my pressure unit, so I'm going to use that 0.821 liters ATMs per moles Kelvin. And then my temperature is 34 degrees Celsius. I'm going to add my 273 right away, so I get 307 Kelvin. Now, if I go through, I can solve for my moles here. Okay, so I'm going to do my PV equals nRT. In this case, I have my 1.04 ATMs. I have my 45.1 liters. That's equal to my N that I don't know. I'm going to use my R, 0.0821. And then my kelvins are 307 Kelvin. So now I'm solving. So algebra says I'm going to divide by the other number. So I'm going to divide by the 821 and the 307. 0.0821 and the 307. So I'm going to figure out what N is equal to. So let's go ahead and get a calculator to do this. So 1.04 times my 45.1 divided by 0.0821, divide that by 307, comes out to be 1.86 moles of CO2. Now the last thing that they wanted though was they wanted this in mass. So now I'm just going to take my 1.86 moles of CO2 and we're just tying it back to something we've already done, which is convert grams to moles. So moles of CO2 to grams of CO2. This is where we look up our molar mass. So carbon is 12.01 plus 16 times 2. So we got 44.01. And so now we just multiply this and we'll get our answer. Times 1.86. So I get 81.9 grams of CO2. So this is just tying us back to what we know about moles and how we can convert moles back into mass. Hopefully that gets you started. You just have a few problems on both Quest and on the practice sheet to do, and we will be doing, I think, a lab in our next as our next activity.